Temperature-compensated programmable current sources discussed in the circuit design video. Output current Iout is relatively independent of temperature. So the first question is how? How does the circuit work? How can we achieve temperature compensation in the circuit? The output current Iout is a function of components in the circuit. So the second question is, what is the formula for the output current as a function of circuit parameters? Let's say we are designing the output current to be in the range of 300 milliamp and 3 milliamp. So how can we achieve that? As soon as we set the value of the potentiometer in the circuit of variable resistor, whether it's a digital potentiometer or analog potentiometer, then that would establish a specific value for Iout in this range. We want it to be a constant or, let's say, fixed, not changing by temperature. So not changing with temperature. That's the meaning of temperature compensation. How can we achieve that? And finally, why we are selecting 3.9 volt Zener diode. So throughout this video, I'll talk about the how the circuit works and also the proper selection or choices, potential choices for the circuit parameters. In this case, we have an unregulated supply voltage, which is, for example, nominal 10 volt. You can select 15 volt if that is your preference, but the message is it's unregulated. It can vary, let's say, from 9 to 12 volt. From that unregulated 10 volt, we have a series of Zener diode, and then in series with one of the two PNP transistors that are paired. So that is, let's say, T3, transistor number 3, that is paired with T2. So T2 and T3 in this circuit are matched, let's say, pair of PNP Bipolar Junction Transistors. And then we have R1 resistor in series with T3 and then connection to ground. So therefore, there is a bias current for Zener diode that is going through the supply and through these three components to ground. That bias current, I refer to it as I Zener, and also it goes this way as well. Okay, for the matched T2 and T3 pair, for these transistors, for example, a good choice would be from Nexperia, as I am showing here, and potentially PNP 5201. As you can see, it's a very small packaged 6-pin with 2 PNP transistor, or BCM 857 is another choice from Nexperia again. So there are many choices that you can just easily purchase them from Mouser or DigiKey. So that's about the matched PNP transistors. For the Zener diode, of course, again, many choices available, both Microsemi and also Vishay, they have good choices. For Vishay, the one that I'm using is because temperature coefficients are available. And specifically, I'm going to talk about the 3.9 volt choice, which means 1N5228. So that one comes with the temperature coefficient of negative 0.06. So what is the meaning of that? To establish the meaning, so that means the voltage drop when properly biased. So let's say we want IZ to be at least 10 milliamp to be on the safe side, so that Zener diode is well biased. Then for that, the voltage drop across the Zener diode, VZ, so that nominal voltage is, so let me put it this way. So the voltage drop across Zener diode has a nominal value, which is 3.9 volt. But then as temperature is changing from, let's say, the room temperature, then the value of this is changing. By how much? By the negative 0.06% per degree change in the junction temperature of the Zener diode. So that's why we say temperature coefficient for this Zener diode is negative 0.06% per, let's say, per degree change. So, or let's put it this way, percent per Kelvin or per degree C. That's exactly what I used here. All right, so in summary, what I get for this Zener diode is it becomes 3.9 volt minus, and if you multiply these guys, you get minus 0. Let's say 234 divided by 100 delta T, which effectively just translates to 3.9 volt minus 2.34 millivolt per degree C or Kelvin times delta T, in which delta T, it's important to make sure that we have a agreement about it. Delta T is just temperature of the Zener diode junction minus the room temperature, which is 300 Kelvin, roughly. So any increase from 300 above will result in reduction of the nominal. Let's say every 1 degree increase from 300 Kelvin of the junction of the Zener diode will reduce the nominal voltage of Zener diode by 2.34 millivolt in this circuit. That's the meaning of that. So this is voltage of Zener diode. So let's refer to this as equation 1. Now, I am going to write the KVL across these 3 components so that I can bias the Zener diode. The main reason to select 3.9 volt, as I'm going to show, is because I would like to have this temperature coefficient of negative 0.06% per degree Kelvin. So what happens is if we write, let's say, the KVL from V supply, we have the sum of Zener diode voltage, then the voltage of emitter base of transistor T3. So this way, that's the emitter base. And then finally, we have the voltage drop across R1, which is simply R1 times IZ. So we have R1 times IZ. Okay, so let's make the assumption that minimum of Vs is 9 volt, because as I said, it's unregulated supply. So let's say if V supply is changing from, say, 12, between 12 and 9 volt in this example, minimum of it is 9, and I want at the minimum, we have proper current for the bias. IZ should be, say, at least 10 milliamp, just desired. So 9 volt is equal to 3.9 nominal plus 0.7 volt nominal voltage for the emitter base of transistor T3, and then plus R1 IZ. Okay, so if I just simplify this, what I get is IZ is equal to 4. So from this we get 4.4 volt divided by R1. That's IZ. And we want it, as I mentioned, to be at least 10 milliamp. So with that, we get R1, this resistor, should be less than or equal 440 ohm. Okay, so that's one outcome. Now, the other KVL I can write is between unregulated supply and the common base of the matched PNP transistors. So on one side, I have just Zener and emitter base. On the other side, I have R2 emitter base, drop across potentiometer, and then emitter base. So these two should be equal to each other. So I'm going to write another KVL, or Kirchhoff voltage law. So if I write another KVL, basically the two parallel voltages should be equal to each other effectively. So we get V Zener, this guy, plus the emitter base of transistor T3 plus voltage of emitter base of transistor T3 should be equal to the R2 times, see this I out is effectively going through this branch because we have effectively a Darlington transistor pair between, say, T1 and T2. Combination of T2 and T1 effectively is in Darlington formation, while T3 is effectively just a diode formation. So assuming T1 is bearing up to, or is carrying up to 300 milliamp, let's say we just set it to up to 500 milliamp at least, it's a let's say mid current size transistor. So the beta, or the current gain for this transistor, which is the collector current divided by base current, is very safe to assume it's at least 50 for the transistor. So this is T1. Therefore, with beta, it means that the base current, so the base current for this PNP transistor is the collector current or emitter current divided by 50 at least, which is the same as emitter for T2, which means is the same as this one, is roughly, or at most, is I out divided by 50. That's why I'm saying we can neglect this current compared to this one, obviously, and that's why I out is roughly the same I out here, which is roughly the same current as here. So emitter and base, emitter and collector currents roughly the same. So I out. Okay, so what do we get now? So we get, or if we want to be accurate, we can just write beta plus 1 divided by beta, or so beta over beta plus 1. So we can say this one here, effectively in this circuit, is just 1 plus, let's say, 1 over beta times I out for this current, because it's an emitter current. All right, so what we get now is R2 times, let's say, I'm going to neglect 1 over beta, so it's R2 I out, and then plus voltage of emitter base of transistor 1, and then plus RP times, again, it would be just simply I out over beta, the current through RP, and then plus the voltage of emitter base of T2, so this voltage basically, VEB2. So with that, I can just write VEB2. Now, because T2 and T3 are matched pair of PNP BJT transistors, they share, because of property of matched transistor, they share the same process, the same junction temperature and properties. Therefore, I just make the assumption that VEB3 and VEB2 just cancel out each other. And I'm going to substitute for VZ using equation 1. So I am going to write that now using equation 1, I can get VZ. I'm going to substitute using what I found here. So 3.9 minus 2.34 millivolt per degree C times delta T is equal to, let's package R2 and RP over beta together because they're both multiplied by I out. So I can have R2 plus RP over beta times I out. And then for VEB1, which is the voltage of emitter base of this higher current, emitter base of this higher current PNP transistor, what I can write is, I can say nominally it's this guy. Nominally is 0.7 volt at when the PN junction is at room temperature. But then it's well known that that emitter base voltage is roughly changing by about 2.15 millivolt negative per degree C or degree Kelvin times the delta T as we talked about. The delta T meaning that deviation of the junction temperature from the room temperature. In this example, we make the assumption that thermally the Zener diode and the matched PNP transistors are just properly connected to each other. Now, the whole idea is almost clear. So if I just nicely rewrite this whole thing, we have 3.9 and then we have minus 0.7. So I'm going to just keep this component on the right side. I'm going to move this component to the left side. So what's going to happen is I'm going to get 3.2 volt, and then we have plus 2.15 minus 2.34, and these guys are in millivolt per degree C times delta T equal to R2 plus, so equal to R2 plus RP over beta times I out. Okay, so that was the whole goal, meaning T2 and T3, the emitter base voltage of these two matched PNP BJT transistor, they sort of cancel out each other. So the temperature dependency of these two are compensated by each other. Now, the negative temperature coefficient of BJT transistor 1 effectively is compensated by negative temperature coefficient of the Zener diode that is specifically selected 3.9 volt. Notice that for other values of Zener diode, we might even end up with positive temperature coefficient that is not helping us, or too much negative temperature coefficient that is not helping us. But specifically in the range of 3.9 for this series from Vishay, the 1N52 series of Zener diode, we get the nice negative 0.06 with the 3.9 volt that, as I said, now end up with effectively these two components cancel out each other. So whatever change is observed around emitter base of transistor P, T1 as a function of temperature is exactly followed by 3.9 volt effectively. So if you compute this, we end up with we end up with roughly 0.19 millivolt per degree C, which is negligible, because even if you multiply it by 100, meaning that even if the junction temperature changes by 100 degrees C or Kelvin, which is a lot, then this whole thing changes only by, let's say, negative just 19 millivolt, which is completely negligible compared to the 3.2 volt. So we are safe. I'm going to basically make the assumption that this one is roughly 0. So as a result, what I get is just 3.2 is equal to then R2 plus RP divided by beta, which is 50 in this example for the high current PNP transistor, times I out. We are almost done because that means we found the formula for I out. I'm going to rewrite this so that the formula is clear. I out is equal to R2 plus I out is equal to 3.2 volt divided by R2 plus RP divided by the beta of the PNP transistor, that is 50 in this case. So beta. That is the formula for I out. Now let's go and apply the range that was given to us. Minimum 3 milliamp, maximum 300 milliamp. So let's try that. So with the minimum current, so let's put it this way, I out minimum, or let's say I out maximum, let's start from that. I out maximum is 300 milliamp. So when do we get I out maximum? We get it when the potentiometer is set to 0, or basically the digital code for potentiometer is set to 0. If this is a digital potentiometer, we know that the value of RP is, and for example, let's take a look at options we have. Analog devices provide us with options like AD8400 or let's say AD5232. These are digital potentiometers, and they are, in the case of AD8400, one channel. Basically, there is one potentiometer there. In the case of 5232, it's a dual channel, so there are two of them available in the same package, independent from each other. There are 256 position, meaning that the value of potentiometer is simply, let's say, the nominal value, which can be any of these choices, 1K, 10K, 50K, 100K, in the case of AD8400, or let's say 10K, 50K, 100K, so that nominal value, say 50K, times, and then the digital code, which 256 is the digital code word, so let's say digital code word, CW. So the value of D is between 0 and 255, and finally divide by 256. So when the digital code word is 0, we get the resistor observed between the two terminals of the digital potentiometer, 0 ohm. When the digital code word is maximum 255, in the case of the 8-bit 256 position, that is the case for both of these designs, 256 and 256, then we get the RP nearly, so effectively approximately the 50K max value. So I'm going to use that for the purpose of the design we had. So in that case, I set the denominator needs to be minimized so that I get the max current. So we get with D equal set to 0, RP, let's say we go with 50 kilo ohm choice, and times digital code word, which is 0 to 255, divide by 256. So using, that's equation 3. So then that translates using equation 3 to RP equal to 0, which means the minimum denominator as we wanted. So I max is then the value of 3.2 volt divided by, this is 0, so just R2. And we want this to be, let's say, 300 milliamp, on that order. So therefore, R2 turns out to be something on the order of 10 ohm. It will give us exactly at least 300 milliamp as the max current. For the minimum current, we want around 3 milliamp. So for this case, of course, we want the maximum denominator, which means RP needs to be maximized, which means D needs to be maximized, and the maximum value of D is 255. So if I set D equal to 255, then RP is roughly 50 kilo ohm, and I out minimum is 3.2 volt divided by R2, which is now 10 ohm. So we found R2, 10 ohm, and then plus 50K divided by 50, because we said RP becomes maximum. So in summary, we get to 3.2 volt divided by just the value of 10,010 ohm, which is roughly on the order of, say, so it's definitely on the order of 15 milliamp. So it's on the ballpark what we wanted in terms of the minimum current we wanted to satisfy. So with that, let me just make sure that the value is accurate. 3.2 divided by 1010, so about 3.16, which is close to what we wanted to realize in this circuit. All right, so we achieved the design with proper selection of components, meaning that we justified why we need 3.9 volt. Basically, it is temperature compensating to a very good extent the variation of the base emitter of T1. And then what's the benefit of having matched pair of PNP Bipolar Junction Transistor T2 and T3, and what are the potential choices for digital potentiometer? In this case, between these two terminals, we selected the value of the 50 kilo ohm for the potentiometer. I hope this example is helpful. Thanks for watching.